Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am super happy to have Dave Clark with us today. Hello, Dave.
Hello, Frank.
First of all, thank you very much for agreeing to talk about your very lovely PSJ article.
Oh, you're very welcome. Thank you for the interest.
It's a nice one. Has some future implications. It'll be cool when we get there. Dave, where are you located at?
Well, I'm in London, Ontario, which is the very southern end of Canada, so about northern California or whatever. So nice and warm here.
Yeah, very good, very good. And it is July 7th of 2023 as we record this, and I imagine it is definitely a nice summer in that part of Canada.
Yes, I'm looking outside at some very blue skies and looking forward to some music festivals this weekend.
Oh, very nice, very nice. So I'm in Phoenix, and the power switch has very definitely been hit. We are hot.
I was just down there a couple of weeks back. Actually, I was in Phoenix and Flagstaff primarily, and
cool.
Beautiful weather. Although the dryness got to me, so I have a bit of a cough. I got water. I've got lozenges here. Hopefully, I won't be coughing during this talk.
No, you'll do great no matter what. And Dave, what is your position there in Ontario?
Well, I am a mature, some would say immature grad student. I decided about 12 years back to pursue a childhood dream and be a scientist.
Very cool. And may I ask what you did before you decided to become a grad student?
Well, I was and continue to be an independent software developer.
Very cool.
I also did some stints in private industry up through BlackBerry and the like, and into junior executive positions there, and then
very cool.
Back on my own again. Yep.
Very cool. Very cool. So let me ask: if somebody gives you a new problem and you reach for your gun on the coding, what is your preferred model? C++?
Well, yes, I've been doing C++ for many years now, and I have been a recent adapted to Python. Python is a phenomenal tool, and so I've integrated all my C++ work into Python, so I can work both ways.
Cool. Very nice. That's awesome. Well, I first of all congratulate you on following your childhood dream, and you are almost there. And I look forward to calling you Dr. Dave at some point. So when do you graduate?
Well, I've always hesitated on saying that, but it has drifted over time. But currently, this is my last paper for the PhD. So currently aiming at defending this fall, and maybe being called doctor in the spring convocation. We'll see.
I'll call you Dr. Dave now. That's awesome. And Dave, what do you like to do for research on the astronomy side of the house?
Well, primarily I'm interested in the things that hit you in the head. The asteroids, smaller objects, and you'll see in this paper that's primarily what it's about. So the smaller meteoroids do have some side interest in comet stream or meteoroid streams, comet dust emanating from comets and such. But basically anything that hits you in the head or is concerned to either Earth as for disaster mitigation or for spacecraft issues.
Exactly. Very cool. Very cool. And that is going to bring us to this very awesome Planetary Science Journal. It is open access. It's the open access era, people. You can go get a copy for free. Go grab one. Preatmospheric detection of a meter-sized Earth impactor. And Dave, take us away.
Okay. Well, thank you very much, Frank. First, I'd like to thank the co-authors, so Paul Wiegert and Peter Brown, Dennis Vida. These are all phenomenally smart gentlemen at Western here, and also Aaron Hines, previously at Atlas, and Larry Deno at Atlas.
Oh, yeah.
They were very helpful in getting the images that I needed, and also helping me interpret the images a bit. Very
nice. Good shout out.
Okay, so what this paper is about, it's I have quite a long-term project that I began in with my master's degree called FROSTY. Every project has to have an acronym, so that's
absolutely
Fireball Retrieval on Survey Telescopic Images. But the idea is that we are looking for
Here it is.
pre-atmospheric images
Okay.
taken of a meteoroid prior to it becoming a fireball in our atmosphere.
Okay.
And what's different with we've all heard of the now 8 instances, I believe, or 7 instances, I believe, of objects being detected in a telescope and then before they hit the Earth.
Mm-hmm.
And then we have the observations in atmosphere, and sometimes in the case of meteorite. This is turning it around and saying we have a fireball observation, and we're looking for serendipitous images that were taken for other reasons.
Got it. Cool.
And they both contribute to the science in the same way, in that being able to correlate the observations that you have in atmosphere with a meteor event with observations of the object in space really allows us to, map one to the other and say, okay, this, and now if we see this in space, we know what it means because we have the same object observed in the atmosphere, and have a different view on that object.
Right.
So so that was the perfect the purpose of this project.
Very nice.
And this paper is about our first successful find of an image.
Nice.
So this occurred on September 18th, 2020. It's an event. It was about measured as a 0.14 kiloton event over the Pacific. Okay, and it was discovered in a very interesting fireball database. It's the CNEOS, that's the Center for Near Object Studies fireball webpage, and there they record or report findings of the U.S. government sensor data.
Mm-hmm.
We have USG data. What those U.S. government sensors are and such, if I tell you, you'd have to kill you. I mean, basically, we don't know.
It's a 3-letter acronym. We'll leave it alone.
But no, but basically, what that means from a scientific perspective is the data is there. It's very useful, but we can't dig into it too much. So we need other sources of data to basically correlate with it. And but so it's very useful. Not always 100% accurate, but and we'll see that in the paper here.
Early on.
Okay, so this object was well, we predicted by looking through a large database of images that we have that this object did appear in an atlas image, and that this object appeared at about visual magnitude 11.5, which is very bright, very bright. And of interest, and unfortunately a little bit of a problem, the image was taken 10 minutes before the fireball hit. So this object was moving very quickly.
Yep.
And what wasn't a scenario that we were expecting. We were expecting to have an object show up in maybe a quartet of images, and we could blink those images and see the object. That was not the case with this. So if we can scroll down maybe a little bit, and we can talk about the actual observation there. So so this is what we get from the CNEOS reporting of the of the USG data, and it's basically what we call the contact state of the meteoroid. So it's the latitude and longitude and altitude of the contact, and its velocity vector.
Escape speeds.
Okay, and of critical importance also is the actual energy that's observed, and that's deduced from the brightness of the object. Okay, now throughout this,
okay, I'm with you. Okay.
Yep. Now throughout this paper, you'll notice that just in order to keep the size of the paper down and the number of tables less, I'll speak to the actual observations, and then later on the right-hand side, for instance, in this table, we did an evaluation of the USG data against other sources of data, and then ended up refining. Okay. So refinements are also in this table as well. Okay, but we can speak to those refinements later.
These are your deltas. Okay. Yes. Okay. And then
so that was the original USG data, and then accompanying USG is GLM. That's the geostationary lightning mapper.
Nice.
2 satellites over the Pacific.
Very good.
Yep. So that gives us another view of the data, and that was the description of the data there. And we'll get into it a little bit further,
Wow.
but a prime part of that is a light curve that comes from it. That helps us again.
Wow, that's a lot. Yeah.
Okay, so the actual image that we predicted. Now we can scroll down to. There we go. There it is.
Big one. Here we go.
Okay, so this is the actual predicted atlas image. That's the red square.
Okay.
And the predicted motion of the object there, that is the white arrow down in the right-hand corner. That was the predicted motion of the object on the image. The green dots just represent an uncertainty cloud that we
Okay.
we computed just based on the reporting accuracies of the USG data. And the blue streaks that you see there, we'll talk about them a little bit later, but those are known satellite paths.
Okay. Okay.
And the white streak on the left, if we actually scroll what that represents, if we scroll down, I'll show you the actual image. We scroll down.
Okay, I'll probably get it in the next one. My answer. Okay, there we go.
Yeah, so there's the actual image, and you can see that that very light streak there. That was actually over on the left-hand side of the image, where we were expecting it to be on the right-hand side. And just up on the top left, you can see as an example one of the satellite streaks.
Yes.
So that's what satellites look like. So you can see that we have to worry about whether we're looking at satellites or whether we're okay. So there's quite a bit of analysis that has to be done there.
And let me just get a sense of the size of this image. Are we looking a couple arc seconds?
5.5 degrees on a side. So it's a large amount of space.
Okay.
Yeah. So we were about in angular degrees, about 4 degrees off in our prediction. Based on the contact to what this streak was. So we obviously have some proving to do to say that this is the object that was observed by.
Sure. Yeah. Because there's a lot of stuff. Very cool. That's a lovely image. Lovely image.
Okay. So now let's see here. So the actual the process involved here is in Frosty is what we do is we do the contact. We get the contact state. We do a gravitational integration backwards.
Okay.
Okay. To see what images are could possibly contain that object. We currently have about 16 million. The paper says 13, but now it's about 16 million image boreholes. We don't actually have the images themselves. We have the image boreholes, the pointings in our database, so that we can search the trajectory. Okay, and so we did, like I say, find this one image. We did actually expand our so we did expand our uncertainties to see if there was a possibility of any other images coming into play, but there weren't. So we concentrated on this one image.
You got it. All right.
Okay. So now if we scroll down to talking about what about this thing? What do we know about this object? What can we learn from this object or about this object? So the fireball properties. So the biggest thing is that we're concerned about is the energy. Like that really gives us a lot of information. And the original USG report was about 0.14 kilotons. And then we can convert that into a mass and such. Another source of information on this was the infrasound, and this is Peter Brown's area of expertise. So he collected the data from an infrasound station in Hawaii, which was about just over 2,000 kilometers away from the event.
Okay. And
this showed us that the predicted energies from USG were probably low.
Okay. All right.
So this object was actually probably closer to a 0.4 kiloton, maybe even 0.6, rather than being a 1.14.
Okay, so you have some.
Yep. So we have some discrepancies there, but and in all of this, it's you're estimating with you're content with magnitudes of error.
Yes.
Yeah,
Yes.
something. But
Understood.
yeah, so we've refined it down to that's somewhere between a 0.2 to 0.7, likely about a 0.4 kiloton event.
Okay.
All right. And if we scroll down a little bit further here.
Sure.
Okay.
Talk about the USG data. Let's take a look at this figure. This is where we're actually.
Yes. This was the
Okay.
this was the actual orbit that we
Okay.
determined the object was coming in on. It will take a look at first in the inner of the two gray orbits there.
Okay.
The original USG derived object. You can see
Mhm.
it was coming in, yes, and see if you can spin your cursor there. Is the direction, it's moving. Yep, the Earth moving up to the right, and
Mhm.
so this object came in from dark sky side, so it was definitely visible.
Yeah.
Okay,
Fair enough.
and the second orbit, as I mentioned, is this is once we adjust our numbers and such. This is the actual orbit that we believe the object came in on. The first one.
Very nice.
Yep, and that's the impact point there. Yep.
Cool. Very
Okay.
cool. Nice.
Scrolling down to table 4, that should.
Let's see. That's one.
That was the
phase angle.
and the actual orbital elements are in a table for a little bit further down, I believe.
Okay, let's look at that. Oh, we got, what do we have here? This is
That's some infrasound information. We'll get to that in a second. Yep.
Okay. So let's go to table 5. Here's our orbital element.
And there, if folks are interested in the actual orbital elements.
State vectors. Yay.
Yep. All right. So if we go back up to and we'll talk about the properties again. So let's scroll back up into section 3.
Okay. Section 3, physical properties.
Yep. Yeah. So that's what we'll pick up there. We'll pick up there.
Okay. Physical properties. Here we go.
So we have this object that is quite moving quite slowly, and yet quite massive. And the other issue that is very interesting is that it fragmented quite high up.
Aha. Okay.
Okay, which is in many ways a contradiction, if you will. So if we can scroll down to there is a section on a figure. I'm trying to remember the figure number now. Oh, okay. Well, there's an interesting there's an interesting one there. If you scroll up a little bit, this is the light curve of from the USG GLM and a simulated light curve if we simulated the fragmentation of this object.
There's a lot going on in this figure.
Yes, there's a lot going on in there. But basically what we're looking at is that the GLM light curve is in the orange.
Okay.
That's the lightning mapper. The original CNEOS light curve is in the blue with much larger error bars, as you can see there. And then a modeling of a fragmentation to meet that, and showing a fragment, showing two levels, two points of fragmentation going on at a high altitude. You see there, well into the 50-kilometer altitude, very high.
Yeah.
Very high
Okay.
fragmentation. All right. Okay. So if we scroll down.
Okay. Very cool.
Go down and looking for. There we go.
Maximum height.
Okay. So this shows us here the many events taken from the CNEOS database and others, showing the typical velocities and the height of the peak brightness, which is what you take as being approximately near where the fragmentation occurs. And the star is this object that we're talking about. And you can see how it is really stands out as being low velocity, high
up when it went through. Okay, these are the pressure isobars where you hit. Okay.
So
okay.
Yep. So what this all leads to is a conclusion that this was a very weak object. because it broke up high in the atmosphere at low altitude. So this wasn't an iron. This wasn't an iron.
Right.
So this was a very loose conglomerate of rubble pile. Yep. And now, if we go to the light curve analysis of from the streak, I think that's the next. Go down again, I believe.
Let's go down to combining the U.S. analysis data. Arc seconds long.
This one there. That's the one I want there. Yep. So this is the analysis of the light curve on the of the streak on the image, the actual streak. Okay, and there's a few things you can notice in this diagram. Number one is that based on just standard meteoroid properties and whatever, to do the estimation of the magnitude of the object, we were coming in at 11.5, and you can see here this is not 11.5. This is 12.5.
Right. Okay,
so this object was darker than what we had estimated originally.
Okay.
And just, I mean, the original estimate is a wild guess, just to try to figure out
ballpark it. Okay.
We haven't seen the object yet. So this shows us again that this object was dark.
Yeah.
Okay, which again means that, well, it's got to be pretty big then, because it's if the object were brighter, it could be smaller.
Yes.
But this case, so this object is, we conclude probably in the 2 to 3 meter range. Dark, very dark albedo. Loose rubble pile. So this is all of a sudden looking very much like 2003 TC3, something like that.
Yeah. So what was the derived albedo on this one?
The derived albedo. That's the stretch. I mean, we discussed it and this has to be an albedo of around 0.02.
Ooh, okay.
Possibly 0.03, but yeah, we're low. It's very low.
Yeah, I won't argue 02 or 03 low.
But it all adds up. You'll also notice in here in this diagram that there is an apparent rotation going on. Yes, and analysis of that gives us, it's a rotation period of about 16 seconds, and you can from the excuse me.
Bless you. Agua time.
Alrighty. The magnitude difference basically gives us a sense of the shape of the object. So we think, about 1.6 to 1.
Okay.
Rotating at about 16 seconds. And if you do the studies of, is that feasible at that rate for a rubble pile? Will the rubble pile fly apart at that rotation?
Right.
No. So this is all consistent. Okay, so we feel that, again, like as I mentioned, just to summarize, we feel we have a 2 to 3 meter object around a 0.02 albedo.
Okay.
And a loose rubble pile. Okay, so now to go to an interesting part of the argument is, of course, is the image that we have and the USG observation the same object?
Fair enough. Yes.
And are they natural objects? Okay, so
that too.
Yeah. So okay, so let's go to let's see. I think we have to scroll up a little bit.
Okay, we covered.
Yeah. Okay. Scroll down.
6.
So we have to combining. Yeah, I wanted to get to scroll down a little bit. I want to get to the combining. Yeah, combining USG and Atlas astrometric data.
Gotcha.
So the question becomes, are they the same object? So what we did was we took the contact state of the object given by GLM and basically started changing 7 parameters. We were feeding this into a Bayesian analysis tool to see so what sort of adjustments would we have to make to correspond to the to the image. So the inputs are
You know?
are the seven points. This is your lon, lat, and altitude of the contact and its velocity vectors.
Okay.
So you take those 7 points and you start varying those. And your goal is to hit the to be able to reproduce the streak on the image.
I'm with you.
Okay, and basically you find the best fit, and then that best fit is what led to our final orbit of the object.
Got it.
Okay, and that
Cool.
okay, and we had the numbers on that. The two important things that come out of it are, number one, the new orbit, but number two is that the adjustments that we had to make are very consistent with the known observational uncertainties from CNEOS and the GLM. Right?
Cool.
I mean, what we're looking at, yeah, we had to change things. We had to change the velocity. We had to change the position a bit, but what we had to change it by was perfectly valid, based on the uncertainties of the observations. So from that perspective, these objects are consistent. Okay.
Cool. That's good.
Or the observations are consistent, yeah. But you can still argue, okay, what was this thing? So let's go down, and there's a few arguments that we had to go through. Yep, that's it, the object origin. So you have the questions around such things as you don't have to scroll up on it, but when we analyze the actual light curve of the object, we were able to do full width half mask around the actual streak on the image, comparing that to the full width half mask of the stars in the image. Okay. And they were the same. So this was a streaking stellar object. So it was the big thing you're looking for there. It's not a satellite. It's not an image of a satellite. Okay, right. That would be out of focus. And so we were content with that. That it's a natural object that the image was. The image was of. But then we also went into an analysis, and we can go further down here. There's an image of the Earth with the Earth's shadow and such.
Let's take a look at that, because I think that's a pretty awesome image, actually. This one.
Yep.
So you get a sense of where actually it came in. LEO limit, low Earth orbit limit.
Yes. So basically, what we're trying to do here is eliminate that this image was actually of a satellite, and so I mean, there are arguments based on its approach velocity or its contact velocity and such that it could have been possibly, if the velocity errors are significant enough, could have been an artificial satellite. Okay. But for that to happen, it would have had to have been inside the Earth's shadow, and therefore would not have shown up on the image.
Yay. Nice. Very cool.
And we took and we also analyzed all of the known objects out there, about 20,000 objects at the time that are being cataloged, and I've shown the ones that were of interest here, and and the only one of interest is the one you can see there, object number 26583, and that's the streak that we see on the image. I showed you back in the original. There was a streak, totally the wrong direction, but
Right.
So so this thing was not a satellite.
Good.
Right.
All right. We have a confirmation, or at least consistency between the two.
Yes. So now the question becomes whether these are, there's a natural object now, but is it the same natural object? Okay, fair enough. And here we went into basically a numerical analysis, if you will, of the Brown et al. 2002 has a very good, concise argument as to how many objects of a given diameter hit the Earth at any given within a year. Okay. Sure. Yeah. Okay. And you can actually directly convert that to an object density. How many objects are there of a given diameter? Yes. Within the Earth environment, and so we did that, and then you just basically, as you move outward, you have to increase your diameter of concern. Yes. But basically, the idea is to determine how many objects could possibly be in an image with the visual magnitude that we detected.
I'm with you.
And it turns into a big, wonderful, beautiful integral that I'll probably publish in another paper or whatever. But
Awesome.
the near distance that you're concerned about is it must be outside the Earth's shadow. So that's like the nearest distance of 3,000 kilometers, and you take it out as far as assuming that the object, being a natural object, was bound to the sun, was heliocentric.
Okay.
Not going to get into interstellar objects at this point.
That's a whole nother ball of wax.
Yeah, but so that you can basically limit how far the object was away by the length of the streak on the image, and so what you do is you integrate. You integrate that across and all the distances, and in the end, it turned out that there is a phenomenally few, about 3.5 times 10 to the minus 6 objects of that visual magnitude in any one atlas image.
Small.
Very small, very small.
So same object.
Same object. Yeah.
Very cool.
Yeah. So that essentially is our conclusion. If you go down to let's see, we'll go down a little bit further here.
Figure 11. Degrees. We got the object streak. And I should have picked that up before. Right. Very good. Then we did the subsequent offset image search.
Yeah, subsequent image search. We did do a obviously we looked again for
okay, yeah.
Now that we had a refined orbit, so now we want to go back and say, hey, has this changed anything? And interestingly, it actually did. The new orbit did get did intersect 2 surveys. A quartet of Catalina sky images that but taken quite a while before the actual impact. And similarly, there was a Zwicky transit facility.
ZPF, I was going to say.
Again, and in both of these cases, though, the object, based on our new calculations of magnitude and such, these objects were simply too dim to be seen in these images. But we did do the visual search. We did spend many times. My eyes went across many times, looking, blinking these images, but no detections on these images.
Okay, well, particularly at that albedo, they're pretty dark.
Yes.
Okay.
Yes. So then down into the discussion section. Here we discuss again. It's primarily summarizing what we've already talked about, but the properties of the object, likely a C-type meteoroid, C-type asteroid, if you will, and coming from the new 6th resonance, and that's based on a Grand Vix model and such. I did do a bit of an analysis just to see. It's not really of great scientific value, but just to see how this compared to the other observations of objects before impact. And unfortunately, in the last few months, we've had this flurry of 2 new objects hitting the Earth that were detected.
Yes.
Prior to those 2, this object from off the CNEOS database was the closest ever observation of an in-space object.
Very cool. Very cool.
Unfortunately, the 2 recent impacts of in last fall and the spring really they eclipsed it very slightly.
But we'll come to that in a minute here. So very cool.
And there is a complete table of all of the objects that have been observed.
Yes. Earth impactors. Here we go.
Yep. So 2002 WJ1 and 2023 CX1. Yeah. Yeah, they both came in at the 11,000 kilometer range, which was the observation range of excuse me.
The one here. Very nice. And then we got some flybys. This is a nice data table. Beautiful. Right. All right.
Yeah, so I think, and then in summary, basically, 2 things. Number one, we feel this project can actually give us some results.
Yeah, there we go.
That's the result wasn't, as I mentioned, of the scenario that we expecting to get a quartet of images and do some blinking, but
that never happens.
And And the other, we were able to deduce some information about this object that
Mhm.
you wouldn't get just straight from the fireball observation. Bringing in the in-space observation,
Right.
able to correlate the two, give you a better view of what this object was all about.
Very awesome. Very nice. Very nice. Dave, I want to thank you so much for sharing your very lovely TSJ article. Thanks.
You're very welcome. Thank you. Thank you for the interest.
Yeah. And you touched on it a little bit there, particularly toward the end. So let me push on that a little bit. On where do you think we go with this, let's say over the next couple of years? I imagine there's still data pipelines going on. Is there other wavelengths one can look at? Is there theoretical work that could be done on these objects? And just sort of next steps, where do we go with this, finding these things over the next couple of years?
Well, I think the biggest thing is the one you mentioned is there's just more data becoming available. There's more people looking. The biggest differences that are occurring, well, first off, there'll be LSST. I mean that is going to be
Huge.
It's huge, right? I mean that's going to be detecting very faint objects, and a lot of them. I mean, covering the sky so often and whatever. And we also have more and more fireball observations going on. I mean, we have sort of the Western-driven global fireball network, and we have and just there's more data on that. So we have more data on both sides, if you will, right? And now, granted, a lot of fireballs are smaller objects. Like we're basically limiting ourselves to 0.2 meter objects or bigger. And we know that a 0.2 object will be visible, at 5 minutes before impact at a magnitude, 13 to 17, which is very visible. Yeah. But you get these small objects 24 hours beforehand, and you're down to 21st, 22nd, 23rd magnitude. That's getting pretty dim. But somebody like LSST will be picking these up, right? I think they can get down to. I shouldn't guess here, but somewhere in the 26.
26 is my memory on that, yes. But it also helped, with the, the number density is a function of size, right? So we'll be able to populate that plot a little bit better on how many are coming in at a given diameter, let's say.
Yeah. And the other side of it that I'm intrigued about is that these objects are sort of at the limit of what we're concerned about inside. Like typically, we're out to we're concerned about the disaster causing objects or whatever, right? These objects are obviously at the low end of all of that, but it does highlight the point of, well, why wasn't it detected? Why wasn't this object detected? Is it because it was too small? Is it because the streak detections aren't working quite well? So I see some value, of maybe a little bit egotistical in saying that, but I think it's worthwhile taking a look at to say, why would we, if we find something, why did we find it? And the survey didn't. That's it.
Correct, exactly, and this is how things get better. Very cool.
Yeah. So and we do. I do have a large database now of fireballs to go through again, and this just the one that jumped out as being right.
Cool.
So now we got to start taking a look at the rest.
Very nice. Well, I look forward to seeing this topic develop over the next couple of years, and I look forward to seeing your next paper or so in the PSJ. So Dave, or Dr. Dave, as it will soon be.
I'm letting people call me that for 2 weeks. After that, that's
it. Okay, I get the early pre-atmospheric one. Very good. Dave, thank you so much once again. And that will do, everyone. And I hope it's made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.